And I'm live. That is pretty cool. Today is 18th of August, 2025, Monday. Yep, today is Monday. And yesterday, after my stream, I did solve a few questions, like 4 to 5 questions, which were easier, which I didn't solve earlier in CP31. But I started to think about the hubris that it would take to think that I could reach a rating of 2000. I started to think that there are people who are smarter than me and they haven't reached that rating. And there are, like, of course, there are good people. There are people who are much better than me at this, and they have been unable to do it. I have a friend in IIT who has been unable to do it. So, what makes me think that I could do it? And that reduced my self confidence quite a bit. But then I thought, isn't this the exact thing that stops people from doing amazing things? The fear, the doubts, the insecurities. And therefore, I decided that however I feel on a particular day, happy, sad, doesn't matter. However I feel, it is just how I feel on that particular day. And such things, such temporary things, should not have permanent effects. And that is copyrighted quote. And therefore, today we will read about number theory, which is cool. Number theory. In the competitive programmer's handbook, I have been unable to understand a few things in the number theory section. Is this number theory? In the starting, there is stuff about prime numbers and yep, about number of primes, density of prime numbers, conjectures, Goldbach's conjecture, twin prime conjecture, Legendry's conjecture, basic algorithms about number theory, right? Finding prime and sieve of Eratosthenes. Sieve of Eratosthenes. Okay. And then Euclid's algorithm. If I understand the basic Euclid's algorithm, which you can use to find GCD, but then there is the extended Euclid's algorithm. And I don't know what this thing is, so we will have to read about it, what this means. We will talk to ChatGPT, we will read articles, and we will do anything that we have to, that we must to understand these things. Then there is modular arithmetic and the basics of it. I am able to understand, but this is also cool. Fermat's theorem, that is also cool. Euler's theorem. This is one thing that I have to understand. This thing uses something called Euler's extended theorem, and that is crazy. Somehow there are a certain class of equations called Diophantine equations. Yeah, Diophantine equations, and to solve them, okay. So there is this thing here called modular inverse. This thing, and I understand the concept of modular inverse. You have to find inverse of some number, let's say x, and if you multiply that inverse with x and you take its modulus with some number m, you should get 1. But the process to find this has to do something with Diophantine equations, and to solve a Diophantine equation you need to know extended Euclid algorithm. It's like crazy cycle. And then there is Chinese remainder theorem, which also uses Euclid's algorithm, extended algorithm, not the basic one. Why do we have Lagrange theorem here? He did a lot of things, I guess. And Zack Snyder, it's Zeckendorf theorem, Pythagorean triplets. You would have to look into that. That and Wilson's theorem. Wait, is wait. This is the first time that I'm seeing this. but I was looking up for number theory books, and there was this book by a guy named Robin Wilson. Wilson. And is this the same thing? Is this the same guy? I think it is. Because this is number theory thing, and he has written a book on number theory. So that is cool. That is cool. And my AC is on now. And we would begin from the start of this chapter, and we would go as far as we can. And the main thing is that we have to achieve is completeness, clarity. I would not skip a topic if I have not understood it. Clarity, completeness, comprehension, right? Clarity, comprehension. Yeah, that is kind of it. Right? Clarity, comprehension, and we will not strive for completeness because these things can take years. So completeness should not be the goal here, but clarity and comprehension. That is a cool goal. So we will start with that. Wait a minute. Cool. Clarity and comprehension. Okay. Number theory is a branch of mathematics that studies numbers, integers. Okay. Number theory is a fascinating field because many questions involving integers are very difficult to solve, even if they seem simple at first glance makes sense. As an example, consider the following equation. This thing. Okay, it is easy to find three real numbers x, y, and z that satisfy the equation. Three real numbers, that is, numbers that contain decimals also, and pi is also real, that satisfy the equation. For example, we can choose these three things. Yep. These are irrational, but they are real. However, it is an open problem in number theory if there are any three integers x, y, and z that would satisfy the equation. Okay, even though this seems simple, we have not been able to find integer solutions to this thing. In this chapter, we will focus on basic concepts and algorithms in number theory. Throughout the chapter, we will assume that all numbers are integers, and if not stated otherwise. Okay, makes sense. And now the first part is primes and factors. And I have read about till the modulus part and also some parts in the modulus part of this chapter, but I want to be very clear with it, right? I have been doing quite a lot of questions, but not enough theory to back that up. So I will also do these theory streams in which I'm just reading, and I would talk to ChatGPT. I would be reading some articles maybe that make me understand stuff, which is cool. And I would have to drink a lot of water. Primes and factors. A number A is called a factor or divisor of a number B if A divides B. Makes sense. If A is a factor of B, we write this thing. Okay, that is the notation. And otherwise, we write it with the cross. For example, the factors of 24 are 1, 2, 3, 4, 6, 8, 12, and 24. A number n greater than 1 is a prime if its only positive factors are 1 and n. Okay, only positive and factors. Factors are things that divide, and only positives are 1 and the number itself. For example, 7, 19, 41 are primes, but 35 is not a prime because 5 into 7 equals 35. For every number n greater than 1, there is a unique prime factorization. Unique, like this. P1, P2, P till Pk are primes, and alpha 1, alpha 2 till alpha k are the exponent to which you have to raise your prime number, where these are distinct primes and these are positive numbers. For example, the factorization of 84 is this 2 square into 3 power 1 into 7 power 1. That is cool, but you have an extra dot at the end. That is also cool. So every number has a unique prime factorization that makes sense. And number of factors of a number is this. This is the multiplication symbol. Like we have the summation symbol. This is for multiplication. I goes from 1 till k. And what we are doing is alpha I plus 1. We are multiplying all of these numbers. Why? Because if I have alpha I as the exponent for a prime factor to a number, then I have alpha I plus 1 ways to choose that number. I could either not choose that number, I could choose alpha minus 1 of those numbers, alpha minus 2, alpha I minus 2, alpha I minus 3 till 0. Right. So in total, I would have from 0 till alpha I ways to choose the number, and in total it would be alpha I plus 1 ways, and I can multiply that with the next prime number, with the next and the next. That is what we are doing here. That is cool, because for each prime number pi there are alpha I plus 1 ways to choose how many times it appears in the factor. For example, the number of factors of 84 is, okay, this is tau 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 84 equals, here we have 3 into 2 into 2. Why? Because 2 plus 1 is 3, 3 into 1 plus 1 is 2, 2 into 1 plus 1, 2. So 2 into 2 into 3, it would be 4 into 12. Oh, yeah, total 12. 4 into 3, 12. The factors are these. Now we could find sum of factors, which is going to be something like this, which is crazy. Okay. So here, this thing means, this thing is when we have pi power, we could take pi power 0, pi power 1, pi power 2 till pi power alpha I, when we have chosen all possible values for its power, for its exponent. And we are multiplying that for every prime number we see. And why is that? Basically draw. Key there, how are you? Which book is this? This is Competitive Programmer's Handbook, CP Scratch. I don't know why I saved it with Scratchbook, but this is Competitive Programmer's Handbook. This book, Competitive Programmer's Handbook. Cool. And why is this thing true? Why this thing makes sense? This makes sense, let's say, because if you have something like this, crazy. If you have something like this, 84 equals to 2 power 2 plus 3 power 1 plus 7 power 1. So in this, at the end, what you want is, you want to choose uh, the number of factors. Let's say you choose in this equation. In this equation here, what we are doing is we are multiplying a few things, and these are the things: 1 plus 2 plus 2 power 2, 4, multiplied by 1 into 3, 1 plus 3. That is how you can choose 3, multiplied by 1 plus 7. And what this means is that this will give you a number of terms. In one term, you can choose this, and this, and multiply them. That would be one of your factors, which is 1 in this case. Then in the second term, you could choose this 2 with 1, which would give you the second factor, which is 2. Then you could choose like any combination, and that would result in a factor, because this is the number of ways, this is the total ways that you could choose 2 as a factor of 84, and this is the total ways that you could choose 3 as a factor of 84, and the same for 7 here. And you are multiplying all of them together to get the total number of ways. And since you have addition in here after multiplication, you would be adding all of those numbers. So that makes sense. And since this is what you are doing, this is like a GP. You start with your base, which is I, and then keep multiplying it by pi. Therefore, the final answer for this summation would be this pi power ai plus 1 minus 1 divided by pi minus 1. That is the summation formula for GP. Now, where the latter formula is based on the geometric progression formula. For example, the sum of factors of 84 is this after finding the GP. The product of the factors, I don't know, maybe in some questions at high level, you might need these things, finding number of factors or sum of factors or product of factors. And this product one is crazy since we calculated that the number of factors for a given number n, and n can be represented as p1 power alpha 1 into p2 power alpha 2 dot till pk power alpha k. The number of factors would be alpha 1, alpha I plus 1, this whole thing, multiply it from I equals 1 till k. That would be the total number of factors. And every single one of the factor would have another number with which it can be multiplied to get this n. And since to get to n once, you are multiplying two numbers. Therefore, you can take the total number of factors, let's call it capital F. At the end, you would be able to make F divided by two number of pairs, total pairs. And each pair would give you a single n. So you can raise n to the power of f by 2. And you would get the multiplication, the product of all the factors, which it is n raised to the power of tau n divided by 2, where tau is the total number of factors. And then moving forward, because we can form tau n divided by two pairs, the factors, each with product n. For example, the factors of 84 and the pairs are this 184, 242, and etc. And the product of the factors would be 84 power 6. Since there are 12 factors in total, you can make 6 pairs. So 84 raised to the power 6 is the thing. That is cool. A number n is called perfect number. A number n is called perfect number if you take sum of all of its factors and it turns out to be twice the number itself. That is a perfect number. Like 12 is a perfect number. 28 is a perfect number. 12 is also a perfect. 12 or 6. I think 6 is a perfect number. 6 has 1. It has 1 as a factor, 2 and 3. And if you add plus 6, you add them, you get 12, which is twice of 6. So 6 is a perfect number. That is good. And like we do not have any practical things, practical applications for perfect numbers. They are just mathematical curiousness. That is all. We do not have any practical purposes in mathematics for these perfect numbers. They are just, when people find perfect numbers, they are just flexing their muscles. That is all. And let me turn off my fan. Yo. And there are 6 people watching somehow. That is crazy. Cool. And ethics, I thought you are a beginner. I thought you know things. And yep, if you are a beginner, then it would be pretty cool to start competitive programming because you will have your highs and lows, and that trains you not just for programming in general, but for life itself. And it is a very worthwhile experience. And now, number of primes. Yes, shit. Okay, okay. This is a very elegant proof. How many number of primes do we think there are? And if we are considering the whole number line from 0 till infinity, is the number of primes that we have, is it finite or infinite? And Euclid, around more than 2000 years ago, Euclid, when was he alive? He was always alive. Like he just died. He was never born. Okay. Uh, Birthday. He 300 BC, so 2300 years ago, right? He proved that we have an infinite number of primes. How? Let's say we have a finite number of primes, which are P1, P2, P3, and till Pn. Let's say we have in total n number of primes and we do not have any primes and we do not have one as a prime. So the first one we can say is 2, 3, 5, and then goes on till our last prime. And we are right now supposing that what would happen if we had a finite number of primes. If we had a finite number of primes, then let's say we would multiply all of them together. P2 into P3, multiply everything together till Pn, and that would result in a number, let's call it x, that is divisible by all of these primes. And if we add 1 to this number, now it will always give a remainder of 1 when I divide it with any of these numbers, any of the primes. It will always give a remainder of 1 because I added 1 to it. And what that means is that this new number is not divisible by any of these primes. So is it a prime? Let's say either it is a prime, all right? If it is a prime, then we have already proved that there are always more primes. But if it is not a prime, then there should be another number lower than x plus 1, which divides this number, right? For this x plus 1 to not be a prime, there must be some other number that, let's call it y, that divides this x plus 1 to make this x plus 1 not a prime. And if that is true, then this y number has to be a prime, because if it is not a prime, if this y number is not a prime, then one of these will be able to divide this, and if they were able to divide this, they would be able to divide this, but they are unable to divide this. Therefore y is a prime. Therefore either x plus 1 is a prime, and if it is not a prime, then this y number is a prime. And we can actually see this. Let's say the only primes we have is 2, 3, 5, and 7. And if we were to multiply these 3, 5, and 7, shit, my maths is bad. 30, 210, and we see that this number is divisible by all of these primes. And if now I add 1 to this number, is this number a prime? I don't know. I do not know is if this is a prime. We would have to see is 211 a prime. Yep, it is a prime. So we have more primes, but this is kind of bad because we know that there are more primes than 7, but we did our formal proof in which we took an arbitrary number of primes, and we proved that either this number x plus 1 is a prime, or there exists some other prime which divides this x plus 1. So that is cool. You are participating in GSOC next year? If yes, then I would love to hear your suggestions. I will participate in GSOC. Don't you have your college and attendance? No, I just don't go there. Like it is not important. They do say to come to college, but I just do not go to college. So that is one thing. And about GSOC, yep, I will do my best to get into GSOC in 2026. But right now I'm just not thinking about it. So that is it. And now density of primes. Given yep, density of primes. The density of primes means how often there are primes among the numbers. Let this, yes, we somehow, this is the notation. We use pi, I guess, because pi is similar to prime. We use pi n to denote how many number of primes there are between 1 and n. So for pi 5, it would be 3, because from 1 to 5 we have 2, 3 and 5 as primes. For example, pi 10 equals 4 because we have 7 also, 2, 3, 5 and 7. It is possible to show that pi n equals n divided by log n, and n increases linearly, but log n is very slow when increasing for big numbers. So we have quite a lot of primes, which means that primes are quite frequent. For example, the number of primes between 1 and 10 power 6 is this, and is this. And if we use our formula, this is the number that we get. So that is cool. And now conjectures. There is a difference between theorems and conjectures. Theorems are formal proofs which have been proved. Theorems are statements which have been proved, like Pythagoras theorem, right? It has a formal proof, or the proof that the angles of a triangle add up to 180. It has a formal proof, and so we know them. But conjectures are statements which we assume as if they are true, but we do not know. We do not have a proof for them. For example, there are many conjectures involving primes. Most people think that the conjectures are true, but nobody has been able to prove them. That is the thing. For example, the following conjectures are famous. Goldbach's conjecture, which is that every even number greater than 2 can be represented as a sum of two numbers where a and b both are primes, which means if you take any number, any even number greater than 2, any even number greater than 2, let's say 12, you should be able to prove this equals a plus b, where a and b both are primes. And for 12, it would be, since 1 is not a prime, we cannot take 11 and 1. So 7 and 5. 7 plus 5 equals 12, and 7 and 5 both are primes. That is cool. And twin prime conjecture, that there is an infinite number of pairs of prime forming p plus 2, where p and p plus 2 both are primes. This is saying, like, we have 5 and 7, where 5 and 7 both are prime and they are next to each other with only 6 in the middle. And then we have 17 and 19, where both are prime and we only have 18 in the middle. So this says that these two make a twin. We are calling these primes twin primes because they appear side by side in the number line with only a single even number in the between, in the middle. And the conjecture said that these kind of twins, there are infinite twins like this. And you can find a Veritasium video on this. Veritasium twin primes. I guess this one. I will rewatch this. This is actually cool. So that is twin prime conjecture, and this one I am not very sure about. Legrand's conjecture, Legendre's conjecture. There is always a prime between numbers n square and n plus 1 square, where n is any positive number. So by the definition, we can say for any positive number, if we take n square, let's say 2, 2 square would be 4, and n plus 1 square, that is 3 square, 9, there has to be one prime in the middle. And in this case, we have 2, 5, and 7. And if we do this for any two numbers, any two consecutive numbers, we would see that there is at least one prime. So that is cool. And I don't know how they would apply in competitive programming. I guess maybe at some higher level they would apply. And now basic theorems. This one is cool. If a number n is not prime, it can be represented as a product A, B, where, okay, this thing I would like to go into and explain. And that would be cool. Shit. Speaking a lot takes a lot of water. I don't know how our teachers speak in school. That is crazy. So normally when we have a number, let's say x, and yep, let's say x is this big. I'm representing x as a box with certain length, and the length is x. And now if I were to find two numbers a and b which add up to make x, a and b, I can start taking a and b from the middle, where we have a equals x by 2 and b equals the same thing, x by 2. And now the normal intuition is that if I were to increase one of the numbers, let's say I increase a, I would have to decrease b. B would become smaller. And the difference, this was, they were like this originally. So the difference, the delta A has to be, the increase in length of A has to be equal to the decrease in length of B. Why? Because they both still need to add up to X. So that is pretty normal, right? When you have two numbers which add up to a certain number, and if you increase one of the numbers, then you have to decrease the other number the same amount to keep their sum the same. So that makes sense, intuitive sense in addition at least. But if you have multiplication, product, then it is kind of strange. Then the middle point shifts. Let's say your number is like this, then your middle point is somewhere, like there is no good way to visually represent it, but it is at a place under root x. Now, because if your number is a perfect square, then under root x is going to be an integer. Let's call it a. And if you do a into a, you would get x. But if you decrease one of these numbers lower, if you take another number, let's say a dash, and a dash is lower than root x, then the other number, the complement which you want a dash to be multiplied by, let's call it b dash, b dash has to be greater than x, greater than root x. And this took me some time to get some intuitive sense. I mean, this makes sense logically. If you are decreasing one number, then you have to increase the other number. And yeah, this does make logical sense. The main caveat is that the middle point is here now at root x, and that is the place where you have to balance your numbers. And the main thing is that these pairs of numbers, a dash with b dash, you multiply these two and you get x. And let's say you have c dash which can be paired up with d dash, and they also pair up to multiply to x, and at the start you would have 1 and at the end you would have x. They would also pair up to multiply and to get x. The main thing which I got from this is that from this middle point of root x, you can never make a pair of two numbers from the same side, which would and multiply and make their product equal to x, because both of these would be lower than root x. Let's say you have c dash into a dash, and both of them are lower than root x. So c dash lower, not even equal. We are explicitly saying that they are lower. Into a dash is going to be explicitly lower than x. They would never reach x. And if you have two numbers from the right of root x, you have b dash greater than root x, explicitly greater, not even maybe equal to or greater, explicitly greater. And you also have d dash, which is also greater than root x. And if you multiply both of them, b dash into d dash, it will be greater than the product of those two root x. And we are supposing that these are positive numbers, therefore we can just multiply them without changing the inequality. We would have b dash into d dash always greater than x. So we can never find two numbers on the same side that make a pair and their product is equal to x. Either their product is going to be way high or lower. So that is the thing. And what this means is that you have this thing x, and let's call this point the middle point. And middle point is not exactly in the middle, because the middle point is under root x, and under root x is generally smaller than x by 2. X by 2 would be somewhere here, and under root x is generally smaller. Because let's say x equals 9, then root would be equal to 3, and half is equal to 4.5, and root is smaller than 4.5. So your middle point is somewhere around here, and you have a bunch of numbers which pair up with a bunch of numbers from here. So what this means, the thing here, that is you have to, every number on this side has a pair, has a corresponding number on the other side that it pairs up with. This means that you can just iterate over all of these numbers, and when you find a factor of x while iterating in this range from 1 to root x, while you are iterating here, whenever you find a factor of x, you can simply do x divided by your factor, let's call it a, x by a, that will give you its other pair on the other side. Then you go and do the same with the next number, let's say with this, and you divide this with x divided by this number, and you would get its other counterpart on the other side. And you do this also with the last element, and therefore you just have to iterate from 1 till root x to get all of the factors of x. And if x is a perfect square, you have to root just till equal to root x. So that is cool. You do not have to, therefore, if you are iterating for a number like 10 power 9, right, you do not want to iterate till from 1 to 10 power 9 to check if it is a prime or not. 10 power 9 plus 7 is a prime, so you do not have to iterate the whole way. What you can do is start iterating from 1 till root of this number, which would be around 10 power 4, 5 into 10 power 4, around this one, this much. And this is doable. This is doable. You can start a loop from 1 till this number. And what you can do is see if when you come out the other side, if 1 is the only number that you have in your running vector in which you are adding the factors, then this number has to be a prime because this had no single factor from 1 till root x. So therefore, this number has to be a prime. And you can even find prime factorization of a number. Let's say you have a number like 84. You start iterating from 2 till root 84. Root 84 power 1 by 2. It is like 9.1. You let's say you start iterating from 2 till 9.1. So for 2, you see that it is divisible. So in your factors array, you can add 2, append 2, then divide 84 by 2 and you would get 42. Then you divide it again by 2, you see that 2 is still a factor. So you append 2 again and divide this again by 2. And now 2 is not a factor any longer. You move on to the next number, which is 3. You add 3, since 3 is a factor, you divide this number by 3. And then you see, is 3 is still a factor? Nope, 3 is not a factor. Then you move on. You see 4 is not a factor, 5 is not a factor, 6 is not a factor, 7 is a factor. You append 7 to your vector and divide this number by 7 and you get 1 at the end. And when you have 1, there are no longer going to be any factors. So this is going to be your array, your vector of all the factors. And you even have the prime factorization. This is unique. All of these numbers will always multiply up to 84, 2237, which is the same as what we saw above. 2237. 2 square means 22. And that was the basic algorithm. And all of this is simpler, right? I have read this chapter till around this point, but I barely understand all of this stuff, this later stuff. After modular arithmetic, my understanding is partial. That is why I am doing this stream, so that I am forced to explain and have a comprehensive understanding about these things. So that is cool. And now back to this thing. If a number a is not prime, it can be represented as products a into b, where a is less than or equal to root n, or b, the same thing that I said here, that if you have two numbers a into b multiplying up to x, one of them is going to be here and the other is going to be on the other side. Product a into b, where a less than equal to b or b is less than equal to root n. So it certainly has a factor between 2 and this is floor of root n. Using this observation, we can both test if a number is prime and find the prime factorization of a number in O of root n time. Yep, that would be the time complexity, since your 2 goes from 2 till root n. You are saying if the square of the current value is greater than n, then you exit the loop. The following function prime checks if the given number n is prime. The function attempts to divide n by all numbers between 2 and root n. And if none of them divides n, then n is prime. So we are iterating from 2 till root n, and if at any point we find a number x that leaves no remainder, then return false. This is not a prime. But if I go through the loop and I never return false, then this is a prime and I can return true. That is cool. The following function factors constructs a vector that contains the prime factorization of n. The function divides n by its prime factors and adds them to the vector. The process ends when the remaining number n has no factors between 2 and roof ceiling of root n. And if at the end n is greater than 1, it is a prime. And the last factor. So here we are doing the same thing that I represented here. This thing, we find a factor and we keep dividing the number by that factor, and we keep adding that factor while it divides the given number. Here factor f dot pushback x, and then divide n by x and see if it still divides, and if it does, then push it into f and do this. And if we come out on the other side and we see that n is greater than 1, then that number value of n that we now have is a prime number. And this thing is actually crazy because here we are checking while lower than root of n, we are changing n in the middle, which which is crazy. And I like to visualize this. I try this with the number 10, right? Initially our n equals 10, and we start iterating for x equals to 2, and we see that x does divide 2. So in our factors vector, we would add 2, and n would become n by 2, which is 5. N is now equal to 5, and we would see, does it divide 5? Does 2 divides 5? Nope. So we would increment and go up to the next value of x, which would be 3. But 3 into 3 is 9, and 9 is greater than 5, which is the current value of n. Therefore, we are going to break out of the loop. What this means is that for the current value of n, whatever it is, does not matter what it initially was, but whatever the value is right now, n, we have no factor of that value below root n, below or equal to root n. We do not have any factor of that value. Therefore, n has to be a prime. And in this case also, we have 5, which is a prime. So we will add that remaining number into our factors, and we see it is correct. 2 into 5 does multiply and make 10. So that is good. And this is the same thing that we are doing. Note that each prime factor appears in the vector as many times as it divides the number. For example, for 24, you would have something like this: 2 to 2 and 3, because 8 into 3 is 24. Now, Sieve of Eratosthenes, which is cool. This is, I guess, also in Euclid's era. Ancient Greek. Yep. Okay, so Euclid was around 300 BC. This guy is 194 BC, 100 years younger than Euclid, and they were born. Shit, this guy was born in Libya and died in Egypt, Alexandria. But Euclid was born in Alexandria, Egypt. Then why are they called Greek? Yep. He also died in Alexandria. That is crazy. That is kind of crazy. They both died in the same place, same city, Eratosthenes. And what this algorithm does is, let's say we have a range of numbers in which we have to find all the primes. Let's say for our range n, which is 100, we want to find all the primes in that range. Then we can create a vector of these numbers 0, 1, and like these are the indexes of these numbers till 100. So the total size of this vector is going to be n plus 1, because this is 0 indexed, right? And if the current number is a prime, we will mark it as 1, but if it is not, then we will mark it as 0. 0, we do not think it is a prime, so 0 is 0 because it is not a prime, and 1 we do not consider as a prime, so 1 is also 0. and then we would start iterating our iterator from x equal to 0. X starts from 2 and we would go up till n less than or equal to n, and we would see in our vector, is this current number a prime? And for 2 we do see that 2 is a prime since it is 1 here. Therefore we would then iterate for another, we will take another variable which would be equal to x into x. We would start from here, and our incremental step would be I plus equals x. We would be incrementing our value by the current prime that we have, and for every number that I equals to, we would put it equal to 0, since that number would be divisible by our current prime, which is x. And for x equal to 2, our I would start iterating from 4, then I plus 2, that is 4 plus 2 would become 6, then 8, then 10, and then we will go on similarly till 100, and we would mark like literally half of these numbers would be marked 0 since they are not primes, and then our x would become 3 and we would see, is it not a prime? It is a prime because here we would initially have 1 for every number, but for every number that is divisible by the current prime, we would put it equal to 0. We have 100 equal to 0, 98 and 4 equals to 0. And for every new prime that we find, here we have found 3 equals a prime, 3 is a prime. So we can start iterating with 3. Now our I would be equal to 3 into 3 initially. And why this? Because this number 3 into 3 is the first number, is the first composite number, the smallest composite number that is composite only because of 3. Because every other composite number before 3, before this number 3 into 3, which is 9, like we could say 8 or 6, or every number that was divisible by 3 has already been marked as 0 by other primes like 2, because right now we have 3 into 2, and I am claiming that this is the smallest number that is composite only because of 3, which is 9. But you could see there was 6, which is also composite and divides 3, but that has already been marked as 0 by 2, because since we went back one bit, this would be 3 into 3 minus 1, 6. And if we go back even further, 3 into 3 minus 2 would be 3, which we are currently at, so we do not do anything with this. So therefore we start with 3 into 3 and we keep incrementing our I with a 3. So after 9 we would go to 12, then we would go to 15 and so on, and mark all of these equal to 0. And then our x would increment and our x would become 4, and we would see from our array that it has already been marked as a 0 when we were on 2, because 4 divides 2 and we started with 2 into 2, which is 4. Right here we started with 4, so it is marked already as 0, so we can skip and we can move on to x plus 1, which is 5, and 5 has not been marked, therefore 5 is a prime, and we would start iterating our I from 5 square. 5 into 5, that is 25, and then I would become 30 till 100, and that is the sieve algorithm. Everything that remains at the end in this array whose value equals 1, that index is a prime. And what you can also do is you can keep a running vector in which whenever you see a prime, you can add this prime number into your vector. And I did this Sieve prime factorization. Yep. Here, factorize. This thing is simply prime factorizing. This is not the Sieve algorithm. Sieve of Eratosthenes, Armstrong, packing Queens. I do not have the Sieve algorithm here, but I do have it here. Primes.cpp. Copy this whole thing and go back here. I can paste it. Why is vector? Okay, because I'm not using stdio. SVD. And bitset. How do I include bitset? Now bitset is included. Okay, in this one, there are actually like two algorithms. There is the Sieve algorithm, for which I have this vector called primes, which to which I append whenever I see if x prime and x is inside my range, then primes dot push back x, put x into the vectors in which I am storing all the primes, and SPF, that is the smallest prime factor. And what this vector stores is for a given index I, if I go to its value, it stores the smallest prime number that divides that number. For example, for 9, I would have 3 because 3 is the smallest prime number that divides 9. And for something like 20, I would have 2 because 2 is the smallest prime number that divides 20. And for something like 49, I would have 7. That is the smallest prime number that divides 7, 49. So that is good. Hello. Sieve of Eratosthenes. And we would read it now. Sieve. And the hubris part is true. Hubris. Excessive self-pride. Crazy. I heard Rust Cole. Rust Cole is a character in True Detective. He once said, think of the hubris it would take to yank a soul out of non-existence, which is a crazy dialogue. The hubris it must take to yank a soul out of non-existence. Shit, that is a crazy dialogue. Sieve of Eratosthenes. The Sieve of Eratosthenes is a pre-processing algorithm that builds an array using which we can efficiently check if a given number between 2 and n is prime, and if not, find one prime factor for that number. Yep. The algorithm builds an array sieve whose positions 2 till n are used. The sieve k equals 0 means that k is prime. You can have your notation, whatever you want. 0 might mean prime, might not mean prime, depending on your implementation. And the value sieve k is not equal to 0 means that k is not a prime, and one of its prime factors is sieve k. That is actually crazy that you can do that. The algorithm iterates through the numbers 2 till n one by one, always when a new prime x is found. The algorithm records that the multiples x, 2x, 3x, 4x are not primes because the number x divides them. And we do that by creating an inner loop like this. For example, this for n equals 20. At the end, we would have the sieve as like this. Since 2 is a prime, we have 0. And depending on your implementation, all of this changes. 0 might mean a prime, 0 might mean not a prime. It depends on your implementation. This is cool. The following code implements the sieve of Eratosthenes. Eratosthenes. The code assumes that each number of sieve is initially 0. Since we are supposing that each number is a prime, and then we are weeding them out, weeding all the composite numbers out whenever we see a prime. Then a loop of algorithm is executed n by x times for each value of x. Thus, an upper bound for the running algorithm is the harmonic sum, this n divided by 2 plus n by 3. Because why does the inner loop run this time? Because if we have x as a prime, it can only go up from n equals x, from x equals to whatever the value currently is, and we would be adding x every time to our value. Therefore, at max, it can go n by x times. Makes sense. And then if you take the summation, it is in log n. And in fact, the algorithm is more efficient because the inner loop will be executed only if the number x is prime. So if our current x is a prime, then we can continue if it is not 0. So we won't even run this inner loop. So that is good. And if you do the maths, some complicated maths, or maybe not complicated, I don't know, maths, then you can figure out that the running time for this algorithm is n log of log n, which is crazy. It is almost n, a complexity very near to O of n. Now, Euclid's algorithm, the greatest common divisor of numbers a and b, GCD a, b is the greatest number that divides both a and b. Makes sense. That is the pure definition of GCD. And the least common multiple a of a and b is the smallest number that is divisible by both e and b. That is divisible by both e and b. For example, GCD of these two numbers is 12 and their LCM is 72. 72 is divisible by both numbers and it is the smallest number that is divisible by both of these numbers, and 12 is the largest number that divides both of these numbers. The greatest common divisor and the least common multiple are connected as this, which is crazy. I posted this in my YouTube posts, which is crazy. This looks crazy. I was once struggling to find the LCM in some question, in some code force question, but now I know. I can just multiply the numbers and take their GCD and divide them, which is cool. And now Euclid's algorithm with the one, little one, which says Euclid was a Greek mathematician who lived in, we just saw, 300 BC, before Common Era or before Christ. This is perhaps the first known algorithm in history. It's cool because it is efficient, it works, right? And we use this thing, which is crazy. Which is that this thing, the Euclid's algorithm. Euclid's algorithm says that if you want to find GCD of two numbers, A and B, the GCD of A and B, GCD of A and B equals GCD of B comma A remainder with B, or if one of them is 0, let's say if B equals 0, then A would be the answer. Wait, you write it on the other side, not like this. This is bad practice, not a good mathematician. A, if B equals 0, then the answer would be A. And okay, so what is the intuition behind this? And there is some intuition. Let me actually show you guys the intuition. Euclid's actual proof, what he actually did. Okay, wait, let me hide my screen for a bit. Yep. I had Thomas Shelby edits maths. Where is the book? Okay, let me look for the book. Euclid's book. Okay, let me share my screen back. Euclid's Elements PDF. Maybe this is the thing. This is the book written by Euclid in which he gave all of his, not all, but quite a few of his things. And the algorithm has been proved here. Shit, it has multiple books. That is crazy. Shit. And this on the left is Greek. This is Greek. This is English. Shit, is the whole book like this? The whole book is like this. Greek on the left, English on the right. It is like some question papers, Hindi on one side and English on one side. Okay, where is the GCD section? Or greatest? We can look for it like this. If there are, okay, I guess that was the thing. This thing, the four no, no, wait. Anyways, what is this? If four magnitudes are proportional, then the sum of the largest and the smallest of them is greater than the sum of the remaining two magnitudes. Yeah, he had a lot of proofs. I think it was, yeah. To find the greatest common measure of two given numbers which are not prime to one another. To find the greatest common measure. Shit, that is crazy. GCD of two numbers that are not GCDs. Greatest common. Yesterday I did saw the thing, but I don't know where it is now. And the actual proof, in the actual proof, Euclid did use lines. He had, or the ancient Greeks had no concept of using a number system because the Indian number system was not introduced to them by that time. Wait, am I already at the start? Did I'm back at the start? Okay. Proof of GCD. Okay, shit, that is a sketchy website. I'm looking for the exact thing that Euclid wrote. It would be crazy to find it. I mean, some other publication. Yesterday I did saw the thing, but I don't know. I cannot find it anymore, any longer. Uh, Greatest common. Okay, we can look in the index. There are multiple chapters. Greatest common divisor of two. Okay, this is not how Euclid did mathematics. He used lines instead of numbers. So this is not a good translation. And it would be really cool if we could just find it. Shit, shit, this is the actual book. I cannot even search in this. Here's the index. Wait, this is not Euclid, this is Euler. Oh, this is Euler. We are looking for Euclid. Shit, so elements of algebra was that. That was also Euler. Okay, my bad. Euclid's elements. PDF. Euclid's elements. The first book of the six. First six books. See, shit, this is one thing. This is something. And this is by Euclid. The elements of Euclid. So these are the proposition. Um, where is the one? Uh, I am looking for the one which has proof for the GCD. Eight. Okay. Where there no such thing as greatest common. We do have something called greatest, and this is not the thing. Euclid. This might be it. Uh, nope, nope, nope. I don't know where I found it yesterday. I was looking for it. Yesterday I did find it. Greatest common. Is this the thing? Uh, to find the greatest common measure of two given numbers which are not. Okay, shit. I am stupid. Okay, this is the thing. This is the thing. This is the thing. To find the greatest common measure of two given numbers which are not prime to each other. That is, two numbers that are not prime to each other, we are going to find their greatest common divisor measure. And Euclid used lines to represent this thing. But the proof that I saw, that proof used vertical lines, horizontal lines, these are vertical lines, does not matter. The proof is this. If you have, let's say, a number A is like this, and you have another number B, which is like this, you want to find the greatest number. Hello, Kakashi Uchiha. You want to find the greatest number that divides both of these numbers. That is the GCD. And let's say that number is X. All right. And let's say since X divides both of them, right? You need a certain measure of X, and you can suppose the same thing is here. A certain amount of X divides B and divides A right here. This covers whole A. So here we have a certain amount of X divides B, and that same amount of X that divides B plus some extra amount of X also divides A, since we are saying that X is the GCD of A and B. Now, since this number divides B and A, this, and we know that it also has to divide this certain length. Why? Because this much is equal to B. All right, this much is equal to B, and since we are saying that X is a factor of B, therefore X will divide this much. And since we also know that X is a factor of A, it has to divide this thing, this B thing, and also this whole thing. Therefore, this remaining thing, this delta, this also has to be divisible by X, because the whole thing is right here, because we have the whole thing is divisible, and also a part of it which we are calling B is also divisible. Therefore, this remaining thing should also be divisible by X to make this whole thing divisible by X. Therefore, you can say, if we are calling this a remaining part delta, therefore this delta part and this B part, which we already know, is divisible by X. These both should be divisible by X, and X should be the GCD of both of these. X should be the GCD of both of these. And why is that? Because if there were some other number that divides A and also divides B, which is greater than X, then that would be the GCD, and that number would also divide this delta and would also divide this B, and that would be the GCD for B and delta as well. Therefore, whatever is the GCD of A and B is also the GCD of B and this delta part. And now, since we have proved GCD of A comma B equals GCD, and this delta just equals A minus B, and B, this is what we have proved. We can go further. We can say, let's say now, if A minus B, if A minus B is smaller than B, then we can write GCD of B comma A minus B. We can just switch it up, right? This thing equals this thing because we have only changed the places of these numbers. So now we can write it as this, and we can apply the same argument here. And we can see GCD of B minus A. Wait, I wrote B wrongly, incorrect. Yep. We can apply the same argument here, and we can say B minus A plus B and GCD this, which is crazy. We just subtracted from B A minus B within bracket, so B minus A plus B, this thing goes here, and the GCD, initial GCD, which was equal to X, we supposed, is equal to the GCD of these two numbers also, because we had this proof. We can extend this proof and we can keep doing this, and we can see that since we supposed that A is bigger than B, here we have 2B minus A, which is going to be smaller than B, because this A is bigger than B. Therefore, let's say 2B is smaller than 2A, and you can take one of these A here. 2B minus A is going to be smaller than A. That is cool. So we are getting a smaller number, and this number A minus B is already smaller than A since we are subtracting. So these numbers are going down, and at some point we would have GCD of 0 with some number X, and at that point this X would be the GCD for our original numbers A and B, which is crazy cool. You can apply this. I did write this. I guess not. Yep, here it is. But let me delete the file, and I will create it again. GCD.cpp, and here return integer GCD taking two numbers A and int B, and let's say if not B, that is if B is 0, then return A, otherwise find the GCD, otherwise return GCD of A remainder B comma B, or B comma A remainder B, and GCD for, let's say, um, this number and this number 35. This is equal to GCD of 10023 comma 35, new line, CD concepts, Clang plus plus on gcd.cpp./out, and GCD is 1. We can give it a little bit of space. And GCD equals 1. That is cool. And if we were to take GCD, let's say 55 and 11, we should get 5. 55 and 11. And let's say, what do we get? We do get 11. 11, yes, 11 is the GCD for these two numbers. 11 divides 11 and also 55. That is cool. So the GCD method works. Euclid's algorithm. That is the thing I just explained. But this thing I do not understand. This thing. I would have to go up to ChatGPT to see that. Hello, Euler's totient function. What the heck does that mean? I would have to look that up. And that is the reason for this stream. Till now, the things that I read, I had already read them and done some research, but now I do not understand these things. So I will be reading them with with you, or I have to do my research now on these things. First is this thing, totient function. Numbers A and B are coprimes if GCD of A and B equals 1. That is the definition for two coprime numbers. If they do not have, if their GCD is 1, then they are coprime. That is, they are prime relative to each other. Then Euler's totient function, psi, this is phi, phi, psi, phi, same thing. And psi of n gives the number of coprime numbers 2n between 1 and n. For example, this is 4 because 1 and 5 are coprime, 1 and 7 are coprime, 1 and 12 are coprimes to 12. Okay, this number gives the number of coprimes for n, makes sense, gives the number of coprimes numbers to n between 1 and n, makes sense. Okay, but why would I need that? The value of totient can be calculated from the prime factorization of n using the formula this, from prime factorization. So I have to find all the numbers from 1 to n which are not a factor of 12. Here 1 is a factor, but 1 is by default co-prime for every number. 5 is not a factor because we have 2, 3, 4 as factors. 5 is not a factor. Then we have 6 as a factor, but 7 is not a factor. 8 is also not a factor, but its co-prime with 12 is 4. So that is crazy. We do not only need numbers which are not co-prime, which are not factors. We need numbers which are co-prime, which is the definition. So 11. The value of psi n can be calculated with this thing. Okay, now first of all, what does totient means? And I understand what this function does, but why do we need it? And why is it called totient? What does totient even mean? In Euler totient function, what does totient mean? ChatGPT is crazy. Let's strip it down. The word totient in Euler's totient function is kind of a special mathematical coinage. It does not have a deep meaning outside number theory. It was introduced in the 19th century by J.J. Sylvester, Sylvester still, Sylvester, a contemporary of Cayley, famous for creating lots of new terms. Okay, I think I have heard this name before. Sylvester, J.J. Sylvester. What has this guy done? English mathematician. He made fundamental contributions to matrix theory, invariant. Maybe in invariant theory, I might have heard about him. Partition theory, combinatorics, other notable students. Mm, okay, I do not know about these people. No, I don't know. I think I have heard his name. Arrowing. I feel like I have also heard this guy's name. Arrowing. Stringham. Stringham was an American mathematician born in Yorkshire, New York. He was the first person to denote the natural logarithm as where uh, to denote the natural logarithm as where is its argument. Okay, in place of the use of in place of is common in digital calculators today. The use of okay, the grammar here is amazing. Okay, totient function. Back to this. Cayley. Okay, so there was this mathematician, J.J. Sylvester, English mathematician, a contemporary of Cayley, and he was famous for making lots of new terms. Here is the story. Euler originally just worked the function psi, which counts the positive numbers lower than n or equal to n that are co-primes with n. But why would n could also, yes, n is also co-prime with itself. Nah, no, n is not co-prime with itself unless n equals 1. 1 is the only number which is co-prime with itself. For every other number, the GCD for that number with itself is the number itself. Coprime, relatively coprime to n. He didn't call it the totient function, he just used it in his theorems. Later, Sylvester in 1879, 19th century, right? 19th century, therefore 1879 gave it the name totient derived from the Latin word tot, meaning so many. Okay, in Latin, tot means so many. Totient or the whole number of. So totient literally means the number of or the total count of this the totient of n, the total number of numbers which are lower than equal to n, integers, not numbers, integers lower than equal to n that are co-prime to n. Okay, that is why it is called a totient function. Makes sense. To be concrete, psi of 9 equals 6 since the numbers co-prime to 9 are 1, 2, 4, 5, 7, 8, not 6, because it would be 3, the GCD of 9 and 6. We see that the totient of 9 is 6. There are 6 such numbers. So the word totient is just a fancy historical label. Okay. Just J.J. Sylvester came up with something. And is Cayley famous? Cayley maths. Arthur Cayley. I think I might be Cali mispronouncing this. This might be Cali, not Cayley. Okay, so that is the totient function. At least we know why it is called a totient because J.J. Sylvester gave it the name totient. Totient means total number of in Latin. At least the tot part means that. And then why is the formula this? And why do we need this? And how is calculated? Yo, hello. Are you solving? Shit, my bad. Shit, you had videos on your channel. Are you solving any problems? What is going on here? Today we are going into theory because I am solving quite a few problems daily, but now I cannot just keep on solving problems. I need theory also. And I'm reading theory here on a stream. What is your current rating? 1300. What is this PDF and where can I find this? Is this just some important theorems and formulas for CP? Yes, this is the standard book for competitive programmers handbook. and you can hit competitive CP and just look it up. There the thing is, and this is written by the same guys who have written the CSES thing, the CSES problem set. You go here and you find all of these questions, which is cool. So these same guys have created this question set and also this book. Wait, and the link is here. No, cool. That is very cool. The definition is simple. Okay, very simple. When now, but computing it by brute force, checking every number is inefficient. The beauty is in how Euler connected it to prime factorization. Prime factorization. Okay, for a number n, we can represent it as p1 power a1, p2 power a2, and where pi are distinct primes. Use Euler's formula, which is this n multiplied by 1 minus p by 1 into 1 minus p by 2 till 1 minus p by m. That would give you the totient. This comes from the principle of inclusion exclusion. Huh? Out of n numbers throughout the multiples of pi. Okay, in total I have n numbers. Wait, is this something like probability? And throughout the multiples of p2 and so on. What remains are exactly the numbers co-prime to n. That is the goal throughout out of n numbers throughout the multiples of each of these primes. That is the main goal. Shit. Okay. Okay. Let's say n equals p1 power alpha 1. Let's say p1, p2, p3, and yes, this is the way I write p, and p4 till pm. These are all the prime factors of n. All right, and in a given range, uh, I would have p divided by n factors of p1. That is the probability to find factors of p1 in a given range. If I multiply this by, let's say, k, then k by p1 would give me around the same the number of numbers from 1 till k which are divisible by p1, and that makes sense, right? So 1 by p1 is kind of like the probability for finding a number that is divisible by p1, but we want to exclude them, so we find the probability of numbers which are not divisible by p1 by using the basic formula of probability, 1 minus 1 by p1. This thing is the probability for finding a factor of p1 or a factor of p1, and if we subtract this 1 minus number of factors of p1, or I think I should write this instead of f, I should use p as in probability. So probability of finding a factor of p1, I subtracted that from 1, and this gives me probability of not a factor of p1, right? And my range is n. So if I multiply n by this probability in a given range of not finding a factor of p1, I will get the number of numbers which are not the count of numbers which are not a factor of p1 in this given range. And I simply have to repeat this process with all of the prime numbers. That makes a lot of sense actually. Probability of not finding a factor of p3 into probability of not finding a factor of p4 dot dot dot, and this goes on till probability of not finding a factor of pm. So that is cool. That is cool. This one makes sense, and I guess this one makes less sense. Like this is kind of this one makes less sense. This is not obvious what they are trying to do here. I think okay, so they do have the series. They are multiplying from I equals to 1 till I equals k. But where is this n? And what have they done? How have they converted this thing into this pi? And why do I have this thing at the top? Okay, I think this is because this formula is more about probability and statistics, and this one gives an exact amount. We can do this for psi equal to 12. We can calculate this for this thing equal for psi 12. We have p1 equals 2, p2 is 3, and there are no other prime factors for this. Yep, for 12. So we do 12 n multiplied by 1 minus 1 by 2 into 1 minus 1 by 3, and this will give us 12 into 1 by 2 into 2 by 3. Yes, and that is actually crazy because at the bottom I would always get one of those prime factors of this number, right? And since it is a prime factor of this number, these number will always divide this 2, and the answer comes out to be 4, which is the same thing as here 4. So that is cool, and I think we can convert this formula into something like this. How? Okay, so our formula is this: n into 1 minus 1 divided by p1, and let's just do this with p1 and p2, where we have p1 power alpha 1 into p2 power alpha 2, and I'm just playing around here. I do not know this, right? And I can, and yes, n equals p1 power alpha 1 into p2 power alpha 2. So now we have p1 minus 1 into p2 minus 1, this whole thing divided by p1 p2, and I can write n as p1 power alpha 1 into p2 power alpha 2, and p1 should, this is becoming similar to the formula that we saw there, this thing divided by p1 p2, and yes, this is p and this one belongs to this p, and then p1 power alpha 1 minus 1 into p2 power alpha 2 minus 1, because of these numbers p1 and p2, and in the bracket we have p1 minus 1 and p2 minus 1. That is cool. That is actually cool, and we can write this as multiplication of I equal to 1 till k, where I ranges from p I power alpha I minus 1 multiplied by p I minus 1. This is the general formula, which is the same that has been given to us in this book. Yep. I ranges from 1 to k, where you do this thing. So we essentially we derived this formula. We have derived this formula from this thing, and that is cool. That is cool. This is the whole derivation, it seems like. Yep, that is cool. And we also know why this formula works, because of probability. And since we have this hypothesis, which we think is correct, we will present this to ChatGPT and see how well it is. But before that, let's read what ChatGPT says about this. I will look at this. Why is this CSES important? CSES helps you. Yeah, cool. CSES helps you because like it helps you. Like in the morning, I was learning or reading about graphs, and therefore I have to do some questions on graphs. I can go to CSES and graphs. I can do graph algorithms. That is cool. I would be doing some of these. And then maybe I would even start streaming while solving these questions. That would be cool. Now this thing, what ChatGPT says. Use Euler's formula, this thing, and we now know why this works, because 1 by p1 is the probability of finding a factor of p1, and if we do 1 minus 1 by p1, that is the probability of not finding a factor of p1, and we multiply that by our range, and we multiply all of those prime factors with our range to get the total number of numbers that are not divisible. And there are some examples on the same, some shortcuts. If n is a prime, then all of the numbers from 2 till n are co-primes, which would be n minus 1 numbers in total. If n is a power of it, if n is a power of a prime number, then that I guess makes sense. Okay, so our theory is this. In the formula, we are taking 1 by p, where p is a prime factor, and 1 by p gives us the ability of finding a factor, a multiple of p, and then we do 1 minus 1 by p, which gives us the ability of not finding a factor of p, and then we multiply that with our range, which gives us with our range n, which gives us the number of the count of numbers which are not a multiple of p in the range n. And we do this for all of the all of the prime factors of n, and in the end we get the count of co-primes of n in the range 1 to n. Let's see. Exactly, you have nailed the intuition. Let me sharpen and expand your reasoning a bit. So see why multiplication works. Cleanly start with all the numbers. Yep, that is our initial range 1 to n. Probability interpretation for a given prime factor n 1 by p of all numbers up to n are multiples of p. So 1 minus 1 by p is the proportion of numbers not divisible by p. Yes, that is what we established. Why multiply the factors? Here is the subtlety. If n has multiple prime factors, all of these we do not want to double count. That makes a lot of sense. That is why we are multiplying from the given niche that we have. From that, like, that makes sense. That makes sense. I didn't thought of that. If we have n, the initial range, then we multiply n by this thing, which gives us from 1 to n the number of numbers. Let's say n is our initial range, and we multiply this by 1 minus 1 by p1, and this thing now is the count of numbers from 1 to n which are not divisible by p1. And now within this range, which is from this numbers, from these numbers, we want to find out all the numbers that are not a factor of p2. That is why we are multiplying. That makes sense. And then this is the amount of numbers from 1 till n that are not a factor of p1 and also not a factor of and not a multiple of p1 and also not a multiple of p2. That makes sense. And then we can repeat this process for all of the numbers, all of the other prime factors of n from p1 till pn. That makes a lot of sense. And that is why we are multiplying. And because we do not want to double count, something like this. Yep. That is why we are not additioning, we are not adding, we are multiplying, because here this is the number of this is the count of numbers which are not divisible by p1, and this whole thing is the count of numbers which are not divisible by p2, and we want to find their intersection and not their union. If we wanted to find their union, we would add them and then subtract their intersection, but we want to find their intersection. That is why we are multiplying them. That makes sense. That makes sense. Then probability, why multiply the factors? Because we are sinking our range. Take n equals 12. Yep. Yep. Makes sense. About 1/3 of the numbers are coprimes to 12. Yep. Connection to inclusion, exclusion. What you did with probabilities is actually Euler's inclusion exclusion argument in disguise. Subtract the multiples of p1, subtract the multiples of p2, and add back multiples of p1 and p2. Multiples of p1 and p2, because when you subtracted the multiples of p1, you also subtracted some of the multiples of p2, and then when you subtracted the multiples of p2, you subtracted more than you should have, because some of the multiples of p2 were already subtracted when you subtracted the multiples of p1. Therefore, you have to add back that in common intersection of p1 and p2. Makes sense. And then you keep going. Okay, I will never stop. I will keep going. The product formula is just a compressed version of that. Yes, your probability viewpoint is essentially inclusion and exclusion turned into multiplication. So yes, yes, we can write it like this. We can actually write it like this. But calculating this is also fine. Calculating this is also fine. We can do this. We can use this formula, or we could use this formula, and I guess I would go with this because here I would already know the value of P1 raised to the power of alpha I. I just have to divide this number only once by P1, and calculating this would be also easy. Then I can just multiply them and then multiply do this same thing for all of I from 1 to k, and multiply all of them together. Okay, why multiplying those factors isn't cheating. Are you satisfied with the probability intuition? I am satisfied. That is cool. Modular arithmetics now. It's been about 2 hours. That is good. Shit. So this is cool. What is the conclusion of this whole paragraph? We know that totient, tot in Latin means the whole of, all of, the whole of, like the count of, as much as of, something like that. And totient means totient of a number, and means all of the numbers and the count of numbers which are lower than n, which are co-prime to n. And there was a guy named J.J. Sylvester who gave this term in the 19th century, which is not very relevant to this thing. But we know a good thing, that is why this formula works and where this formula comes from, which is cool. Which is cool. Let me rewrite this formula once more so that I remember. Totient phi, we have two formulas for this. The one that is given in the handbook is I from 1. We iterate from I from 1 for pi alpha I minus 1 into 1 into pi minus 1. We do this and we get the totient of a number n. Cool. There is another formula, probability formula. This is also the probability formula, but this has been changed a bit, which is equal to n multiplied by, not shit, this is not summation, my bad, this is not summation. This is multiplication, pi, which is represented by pi. Here we have n multiplied by multiplication of I equals 1 till k, and inside we are multiplying 1 by p divided by 1 by 1 minus 1 by pi. That is another formula, and these are interconvertible. We can convert them into each other. So that is cool. That is cool. That is the totient function. Now, listen, and this, I guess, took more than 30 minutes. This took us more than 30 minutes to understand this one paragraph. This is fine because now we do not have to reread this again. We know what this means, what the totient function is, what coprimes are, and why this formula works. We know that. So that is cool. Now, modular arithmetics. Prisma X. Hey bro, should I go on solve the USACO guide or do random practice and learn these topics which I encounter, which would be best? Well, for me, I try to read the competitive programmer's handbook, right, mm, as a schedule thing. And I also have another book, CLRS, this one, which I try to read, but that does not actually work because even if I read about an algorithm and I do not know where to apply it, I would not be very interested in that. So what I have switched to is, while I'm solving these questions on CP 31, whenever I encounter something that I do not know about, I will have to read about it. Like till now, yesterday, I was unable to solve, I guess, this question. Yesterday I was unable to solve this question on stream, right? Yep, time limit exceeded. And because this question used graphs, and to be more specific, I had to use mm, depth first search, and I didn't know about depth first search. So after the stream, I went on to this book, and here I read about this thing, graphs, depth first search. I read about this, and then I implemented the algorithm, and I got my answer submitted. So that is cool. That is what you can do. And since I know a little bit about graphs, I would now go on to CACS and solve a few of these graph problems. That would be cool. So yeah, you should go and do questions which would be the best. Do not look for the best. Do not look for the best. Pick anything and move forward. Which is the best? Which is actually the best thing? Pick anything and move forward and make incremental progress. So yeah, solve questions, and whenever you see a new topic, go read about it, and from different sources, read about it from Competitive Programmers Handbook, or you can go to YouTube, watch some Abdul Bari lectures, and there is also CLRS, which is the book. This is not one of the books. This is the book. You can go and read about the thing here, and then go and do some problems on that thing, which is cool. And yes, modular arithmetic. I struggled with some questions which have to do with number theory. That is why I am also reading number theory, but I was not able to go past, like, I do understand this much. The thing that gave me problem was this much, this part. Like, why does this thing work? And why was this guy, Fermat, why was he even doing mathematics? Because he was a French lawyer. He was a lawyer. Fermat was a lawyer. Why was he even doing mathematics? And yeah, there is a story behind Fermat, which is crazy, which I will get into in a bit while we get to that. And now modular arithmetics. The videos that I have seen, watched on modular arithmetics, they say that if I am dealing with modulo k, let's say, then I should think of it like this. I have a clock which starts at 0, 1, 2, it goes on till k minus 1, and every number can be represented, any number from 1 till infinity or even minus infinity can be represented on this clock in these at one of these places. For example, if we are dealing with mod 7, then our clock would have 0, 1, 2, 3, 4, 5, and at last 6. And if we want to represent 10 on our clock, remainder of 10 with 7 is 3, so 10 comes here, 10 would be here, and if we, let's say, take any other number, 15, remainder for 15 is 1, so 15 comes here. And if we now do 10 plus 15 and do mod 7 on this thing, that would be, here we have 1 for 15 and we have 3 for 15, and we are adding them, so we just add 1 and 3, and we should get remainder equal to 4. And here this thing is 25 and the remainder is 4. Remainder is 4 because 21 is divisible by 7 and 25 minus 21 is equal to 4, so that is cool. Let's say you now do something like 4 is also on at this place because 4 mod 7 is also 4. That is crazy. And if we have something like 6 would also come here. Let's say not even 6, 20. 20 would also come here because 20 modulo 7 is 6 because of 14. 20 minus 14 is 6. So we have 20 here. And if we were to do 20 plus 4, 20 is represented as 6 and 4 is represented as 4. We add them, which is 10, and we saw before 10 is represented as 3. So the answer should be 3 if we take modulo. So 20 plus 4, which is 24, and if we do 24 mod 7, that actually is equal to 3 because of 21, 24 minus 21, it is 3. So that is cool. So the things just go around this circle. But for multiplication, for subtraction, it is kind of crazy. And for multiplication, it is also fine. If I have 6, if I have a number which is represented as 6, and if I have a number which is represented as 2, which would be 16, something like 16. And if I were to multiply these two numbers, that is 20 into 16, that would be 320. And if I take modulo of this thing with 7, which would be, I have 280 and then 40, 35, 315. The modulus should be 5, right? 5. And we have this thing is represented by 6. This is represented by 2. So 6 into 2, which is 12. And if we do 12 mod 7, we get 5, which is the same as we got here. So multiplication just works as you would expect. But division and subtraction is crazy. Let's say you have back way. Let me create another circle. That one got clunky. And if we are working with something like 11 would be a big thing. Let's go with 11. 11, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and the last one would be 10 till 11 minus 1. And if we have on this thing something with a remainder of 2 would be 13. 13 would be represented here at 2, and something with the remainder of 10 would be 21. 21 gives a remainder of 10. And if we want to find the remainder of 2, uh, okay, this is not a good example. Good would be 24. Let's take 24 here, right? Right, 24. If we have 24, because 24 also gives a remainder of 2, with 11, because 22 is divisible by 11. So we want to find 24 minus 21 modulo 11. And just by looking at it, we can say that it is 3, right? Because makes sense, right? 24 minus 21 is 3, and 3 modulus 11 is 3. But if we wanted to find it with this, then we would have this 2, because 24 is represented by 2 here. So 2 minus 21 is represented by 10. So 2 minus 10 mod 11, that is minus 8 mod 11. And what does this thing mean? For this, we have to see what does mod mean. When we are taking mod with m, that means if I'm taking mod of some number x with m, And if that turns out to be, let's say, y, then what this means is that there is some number a. If I multiply a by m, I will cover quite a bit of x. X is this whole number. X is this whole number. And the remainder that I would get, it would be y. The remainder that I would get, it would be y. Because that is the definition of this thing. That is the definition of modulus. Because if I were to extend this to a plus 1 into m, it would go past x, which is bad, right? We want the remainder. But even if it goes past x, we can represent this boundary. How? Because from this, we had to add a positive number y to this to get to x. But now from this boundary, we could say we have to subtract a certain number from this thing. And what would that certain number be? It would be, since we know that this distance is m, and this would be the actual modulus, this would be the certain number that we have to subtract from m. Total is m, this is y, so this would be y, and we can call this b. Let's say b equals b, and what we have here is this certain number. So if I do, I guess, m, and this number is negative, this number is negative, this is plus, this is negative, because we are subtracting, we have to subtract from this, this has to be negative. So if this is my answer, then I can just do 11 minus this number, or just add this number 8, that would be 3, which actually is the answer that we got here, 3. So if you are getting negative as modulus for some number, then you have to just add m to it to get the actual modulus. So that is cool. That was the only thing in when the modulus turns out to be negative, or when you are taking difference of two numbers, not difference, when you are subtracting two numbers and taking their modulus. That is the thing that you have to keep in mind. And for addition, it is cool. For subtraction, it is cool. For multiplication also, it is cool, as we have seen. And for exponent also, yep, you take the modulus of the number and you raise that modulus to the power n, and then you take the modulus of that thing that you got. So that is cool. Nice. Are you using mic? Yep, I am using mic. Okay, what mic am I using? I don't know. It is, I guess, the cheapest mic I could find on Amazon. Yeah, I guess it is around 250 or 300 rupees, the cheapest I could find. And in the future, if this thing becomes big, the goals are to buy something like this. Shure microphones. This is expensive. This is expensive, but this is the standard thing. This is used by Lex Friedman and the people in podcast thing. This looks cool also. So we are done with that, and now modular exponentiation. And yes, this is cool. This is cool. Let me actually show you. I think I wrote something on this. X exponent. No, delete, and we are defining our own number, our own function called pow, which takes in a number and raises that number to a power of e. And if e, if not e, that is if e is 0, then return 1. Otherwise, we could just say int, or let's make it long. Long I equals power of n with e by 2, and after that return I into if if n is odd, then multiply by n, otherwise just return it like as it is, and this should work now. If you were to find power of stuff like this, let's say 2 power 12. What is 2 power 12? 4048, because 2 power 10 is 1024. 4048, this should be 2 power 12. Let's see what that turns out to be. Is it, oh, yeah, I was in the terminal already. Line plus plus exponent dot cpp out dot slash out. It turns out to be 1. Actually, shit, that is crazy. And exponent dot cpp, and if not e, then do this, otherwise power this, and this y, is it 1? Is it because it is long? I can make it an integer also if you want, but that shouldn't be a problem. The data type should not, yep, data type is not the problem. 2 raised to the power I 12. Raise it to half of its power. And then I into if n is odd, then multiply it by n, otherwise multiply it by 1. Makes sense. So for if I do square, then n would be 2, e would be 2, and this is false, e is not equal to 0. So I would call this power function again, which would do n equals 2 and e 1. That makes sense. That makes sense. So when I am trying to find power when e equals 1, then return n. Makes sense because I was never returning n. That must have been a problem. That even that should not be a problem, because even when I'm doing this, let's say, and I call this again n, in this would be equal to 2 as it is, and e by 2 would become 0. So when not e, I would return 1. So this function I would be equal to 1, and then I would do 1 into 1 multiply by n. If n is odd, then multiply by n, which is 2. So I should have gotten some answer. Line dot slash out, but I do not due to some reason. So if odd, then multiply by this, otherwise multiply by this. So this thing turns out to be false, because we have to see if, yeah, makes sense. E, this has to be E. Now 2, 12, blank, and I should get to 4048. 4096, my bad. 4096, 4096 makes sense. It is 2048. Yeah, 10 power, 2 power 11. 2 power 11 is 40. 2048. 2048. Cool. And now I will go to the washroom and I will be right back. You me right back. Yep. And we would just move on with this. Yep. And this is the thing that is explained in this part. And this is actually the exact code they are also checking for. Okay, they have taken a modulus with which they are finding the value. That makes sense. That is why modular exponentiation makes sense. This part was actually not necessary. 1 modulus m. If m is 1, then this thing should be 0. 0 would be returned. N is the exponent and x is the base. Long u is 1 power and n by 2 for with modulus m. U is u into u by this, and if it is even, then multiply it by x again and take its modulus with m and return u. So that is cool. Because you have 2 power 12 equals 2 power 6 into 2 power 6, right? Which in turn is 2 power 3 into 2 power 3. I'm my bad. No, this is correct. This is correct. 2, because 3 plus 3 is 6, and this also 2 power 3 into 2 power 3, and then 2 power 1 into 2 power 2, 2 power 1 into 2 power 2, 2 power 1 into 2 power 2, and same for this one into 2 power 2. So you just multiply all of this, get this, which is cool. And also you are always taking modulus, which is cool. Well, this thing would not actually help you in like saving time complexity, because you are actually calculating the same thing again and again. You're not using any memorization. So you are, whenever you need a 2 power 3, you are actually calling the function again to find 2 power 3. So this is not efficient. The main idea is that mod m is about mod m. You will find 12 power modulus m. That is, it does not exceed the value m, because you are always taking modulus of that number with m. Another thing, yep, Fermat and Euler's theorem. This is the crazy thing, and this is the crazy thing. This thing, Fermat's theorem, it says that you have some number and you are taking mod m, where m is a prime, and if m is a prime, you can take any number x which is smaller than m and raise x to power m minus 1, and if you take modulus of that with m, you will get 1. That is what he says. If we take m equals 7, which is a prime, and we take any number x which is smaller than 7, let's say 5, and if we raise 5 to power m minus 1, that is 7 minus 1 is 5 power 6. What would that be? 625 into 25. It would be something like 25, 3, 1 into 5, and then 1, 5, 6 to 5. Yep, 1, 5, 6 to 5. And if you take mod of this number with 7, 1, 5, 6 to 5. If you take mod of this number with 7, you can take mod with this much, you would get 14, 1, 6, 2, 5, 0. Then you take mod with this with 2, 2, 5, and again 1, 5. What shit, it turns out to be 1. It is actually 1. So Fermat was on to something, even though he was not supposed to. He was a lawyer. Fermat was a French lawyer. Pierre de Fermat, French mathematician, and he was a lawyer actually. Like, Fermat lawyer. Yeah, he was a lawyer, and he is not remembered for his law thing. He is remembered for his maths thing. He used to do maths in his free time. Shit, his wife's name is Louis Long Fermat, and she died, but we don't know when she was born. And yeah, Fermat, there's a whole story behind him which you can watch on number 5. Number 5. You can, yep, this video, you can watch this video. This is crazy cool. And yes, this exact thing, x power n plus y power n equals z power n, and any for any value, for any n which is greater than 2 in this thing, you have x power n plus y power n equals z power n for any n greater than 2. This thing has no integer solution, like literally not even one, no integer solution. But for smaller powers, you could take yep, and no positive integer solution, I guess, because if you were to take one of these as zeros, then the other one you could take y equals z and you would have a solution. So I guess you cannot take 0, or even if you take, they have to be distinct x, y, and z. That would be the condition. Yeah, that is cool. There is no solution for n greater than 2. But for n equals to 2, I think we right here should be able to find some solutions for this thing. Z square, and if you take x equals 2, we would get 4 here, and yes, we can do binary thing. Let's say we are going to take this as a multiple of 2. Then if nope, with 2 it would not work. It would not work because we could also take this as 2, right? And we would get 4. Then the sum would be 8, and then we could take this. Nope, this is not going to work for x equal to 2. uh, solution for x power 2 plus y power 2 equals z power 2. Anything, yep. Integer solutions. Where are okay, these are the solutions. That is good for this one, but for n greater than 2, there are no solutions. That is Fermat's last theorem. And there is also Fermat's little theorem, which is this. I think this is Fermat's little theorem. Yeah, Fermat's little theorem. You can also write this like this, which simply says you have modulus of a power p with p is equal to the modulus of a with p. And if you divide both the sides with a, you should get here 1 and you should get here p minus 1, a power p minus 1. But division is bad. Division is bad because to divide with modulus on both the sides, you need to take its modular inverse, like which we will get into in a bit. Okay, so this is Fermat's theorem. This thing, this thing. This is Fermat's theorem, little theorem. And yep, where m is a prime number, x and m are co-primes. Okay, that makes sense. X and m have to be co-prime. X and m have to be co-primes. If x and m are not co-primes, they would have some number that divides both of them. And yeah, if they are not co-prime, then no solution. If x and m, we have two numbers, x and m. M is a prime, m is a prime. And if x and m are not prime, then let's say x into y is some integer, plus k into m, k is also some integer, cannot be equal to 1. Cannot be equal to 1 because if they are not co-primes, because the smallest distance that we can have between some integer multiple of x and some integer multiple of m is never going to be lower than their GCD. It is at minimum going to be equal to their GCD. Not even at minimum, it is going to be a multiple of their GCD. We can say n into their GCD of x and m, which is crazy, which is Euler's form, which is how we find modular inverse. They will have the same thing here later. Okay, then where is it? And this is one of the Diophantine equation, which we can solve using extended Euler's algorithm, extended Euler theorem, which we would have to look up. So this thing makes sense. This thing makes sense, right? This makes sense. If x and m are coprimes, then x raised to the power of m minus 1 mod m will give 1, where m is a prime. X power k. And what is this? Okay, this thing can be somehow translated into this, which is x power k mod m. X raised to any random power k mod m equals x raised to that random power take modulus of k with m minus 1 and raise x to that power. Okay, so this is witchcraft tree. We know this, and this also makes, we do not know why this works, but we can expect, right, that this works. And Fermat was such a genius that he used to look at numbers and say that, of course, this thing, right? Of course, this makes sense, right? Of course, this makes sense. That is how he used maths. And he had a book. He had a book, and while he used to read that book, he used to read math books, books with equations. He used to read them, and he also had a pen, equivalent ink pen, that he used to use in like earlier times. And whenever he, while reading the book, he, if he got some idea, he would scribble down that idea on the side, on the margin of the book. That was his way. And when he died, his son gave all of his books and notes to someone who was mathematically inclined, and that person published all of these side things as encryptions in the book itself, like a commentary by Fermat. And that is how we know Fermat's last theorem. It is called Fermat's last theorem because we have not been able to prove it. But Fermat didn't prove his theorems, so we prove his theorems, mathematicians, and we have been able to prove a lot of his theorems except the last. And actually, I think we did solve, we have proved Fermat's last theorem. A guy named John or something, John or Will, who, Fermat's last theorem, Wiles, Andrew Wiles, he solved Fermat's last theorem, which is crazy. Tanimiya-Shimura conjecture, modularity theorem. He used p-adic numbers for his proof. Yeah, crazy stuff. There is a Veritasium video on it. And now, more generally, Euler's theorem. This is the thing that I do not know about. Well, at least we understand the psi function. The psi function with a number m gives the number of cofactors, coprimes of m from range 1 to n. And if we raise any number that is itself coprime, okay, when x and m are coprimes, which itself is a coprime to m, if we raise that number to this thing and take its modulus with m, we should get 1. Fermat's theorem follows Euler's theorem because if m is prime, then this thing is m minus 1. Makes sense. Makes sense. Okay, so shit. So did Fermat cheat? Because Fermat was around 350 years ago and Euler was 2000 years ago. So that is cool. Why does this work? Okay, we might not be able to answer why, but I want to get some intuitive sense why this thing works. X raised to the power psi m, where psi m is the number of co-prime numbers from m, from 1 to m, which are co-primes with m, right? Uh, Toyota function, totient function, totient of m. Should it went below? Totient, totient of m psi. And we have to see why this thing works. Okay, for which we are going to go to ChatGPT. Scroll codes. I have also got this book. Is it good for beginners? It is not. Yeah, it is good in the sense that you know that there are these things which you can read about. Like I might not be able to understand what modular inverse is just from this one page of explanation, and I certainly would not be able to understand what Euler's theorem is just from this small snippet of its description. But I know that there is something called Euler's theorem, and I can go to ChatGPT or other places and read about it. So that is the main thing that comes with this book. And here is this live related to programming. Yep, it is, because you need number theory in competitive programming. That is why. Fusion. And now we need to find out, at least get some idea why this would even make sense. And before moving on with this, I would like to establish that we are on the same page with this. Here we have M. M is a number, any number, right? M is any number, and X is a number that is smaller than M, or it could be bigger than M. Yeah, X is some other number. And the thing is, here X and M are co-primes, which means that they do not have any factor in common except one. Something like 3 and 5 or 6 and 7, they are co-primes. And then we have x raised to the power of psi of m, where psi is the totient function and psi gives the count of numbers from 1. Psi of n gives the count of numbers from 1 till n that are co-prime with n, co-prime with n, the count of numbers. And this formula says that if I raise x, which is a co-prime, to this power and take its modulus with m, I should get 1, which does not make sense, right? Why would it work? Why would it work? Like, does not make sense. So, in the Eulers, but we have x raised to the power of, how do I print psi? Guess, so that is crazy. Let me experiment. I want to print psi. I'm seeing how could I do that. I can print something like this, but I guess this is not psi. Okay, let's take, suppose that it is psi. So we have x raised to the power of psi of m and take its mod with m. Can put this like this equals 1. Here, why does this thing works, and is x and does x have to be lower than m? I don't think it has to be lower, but why does it work? That is the thing, right? Why would it work? Why does it make sense? The statement is this: Euler's theorem says this, and this is actually crazy because Euler didn't know about the numerical representation of algebra that we use today, this Indian representation, which we call uh, Arab representation, because this was taken when the Arabs came to India. They took this representation and spread it outside of India, but this was invented in India. So yeah, and I guess it is called Hindu representation. Yeah, provided that GCD of these two is 1, that is they are co-prime and m is greater than 1. greater than or equal to 1, so that m is not negative. Makes sense. Notice the condition is co-primeness, not x lower than m. Okay, if x greater than m, you just reduce it to modulo m. Reduce it modulo m first. Makes sense, because in modular arithmetic, x is equivalent to x mod m. Makes sense. So x can be bigger than m, no problem. Makes sense. Why does it work? The idea is group theory in disguise. Let us show both the intuitive and formal angle. Okay, in group theory. Okay, yes, of course. And it's been 2 hours and 40 minutes. Okay, let's complete this thing. Euler's theorem and maybe even modular inverse. Because if we can know this, then we can know this. This would be very easy after this, if we can just understand this. And even though I do not want to study anymore, we would push. Why does it work? Yes, the idea is group theory in disguise. The intuition. Take all the numbers that are co-primes to m. Yes, which is this, exactly this, and lower than m. Call this set this thing. Okay, okay, okay. Now multiply each element of u by x. Now multiply each element of u, this thing, by x mod m, x remainder m, because x is co-prime to m. Multiplication by x just rearranges the elements of u. It doesn't throw in a non-co-prime. It doesn't throw in a non-co-prime. That makes sense because it does not even rearranges the numbers. Okay, that makes sense because of because what we did here when we were looking at the circular representation, we saw also about multiplication. And if I have a number which is represented by 1 in modular sense, in modular arithmetic, then does not matter with which number I am multiplying this number with. It will always yield this remainder, right? That makes sense. And since we know that x and m are co-primes, therefore x is going to be represented on this wheel as 1, and yes, if they are co-primes, if they are co-primes, okay, shit, okay, there is a difference between being co-primes and their GCT, and there is a difference between being co-primes and remainder being 1. This is modular thing, and them being co-primes simply means that there is no number bigger than 1 which divides both of them. Yep, there is no number bigger than 1 which divides both of them. And the fact that one of them is like this is different. Makes sense. Makes sense. Okay, let's go to ChatGPT. What it was saying. Okay, this is the set of elements. And this set of elements, all of these numbers are smaller than m and are co-primes with m. Makes sense. They are co-primes with m. Okay. Now multiply each element of u by x mod m, because x is co-prime to m. X is co-prime to m. Multiplication by x just rearranges the elements of u. rearranges. It doesn't throw in a non-coprime and it doesn't create duplicates. So this equals this mod m, multiply all the elements in each set, factor out x's. uh, Okay, so here we have conjunction between two concepts, between modular and being coprime. Okay, let's take an example. For 12, we calculated that alpha 12 equals 4, where the set of U would be 5, 7, 5, 7 coprimes, 11 is also coprime, and 1 is also coprime, right? We had 1 there, 1 is also coprime. Yep, 1 is also coprime. 1 is coprime with every number. Okay, so okay, these are the numbers that are coprime with 12. Okay, and if I take mod of these, they would just still be the same. 1, 5, 7, and 11. And if I have another number, let's say 13, which is a coprime, ChatGPT says this will just shuffle these numbers left to right and not really do anything. So if I multiply 13 by instance of modulus. So modulus of 13 with 12 is already 1, but let's move on anyway. 13, if I multiply 13 by 1, that is 13. Shit, 13 by 5. What is that? 65? Yes, 50, 59. Shit. 18, 91, I think, maybe. 70 plus 21, yeah, 91. And 11, 143, because 130 plus 13. And if I were to take modulus of all of these numbers, ChatGPT says I would get a 1, a 5, a 7, and a 13. A 1, a 5, a 7, and a 13. Let's see. And we would try to find a general proof of why that would be if that is the case. So for 12, the modulus is 1. For this thing, it is 65. Makes sense. 5 because we have 60 divisible by 12 and 65 minus 60 is 65. For 91, we have 72, 84, 7 is still the modulus, and for this we have 11 as the modulus because 144 is divisible by 12. The modulus is same in this case, because if we go back to the modulus wheel after 0 here at 1, if this wheel is for 12, then 13 would be represented here, and does not matter with which number I multiply 13 by, I would always get that same remainder back. So okay, so let's choose some other example. 25 is cool, we can choose 25. Yep, let's choose 25 instead of this. 12 is 1, 5, 7. Shit, 25 also leaves a remainder of 1, so no, that would be bad. Something that leaves another remainder, 3, 4, 5, something that leaves 17. 17 is cool, we can use 17. 11. If I take 17, which is a co-prime with 12, and leaves a remainder of 5, therefore it would be represented if this is 2, 3, 4, 5 around here in the modular arithmetic wheel. And let's multiply. 17 by 1 is 17. 17 by 5 is 50 plus 35, 85, right? 17 by 5 is 85, and 17 by 7 would be 9, 4, 1, 1, and 1, 8, 7. And the modulus here is 5 because 17, 17. And here the modulus with 12 is 84, 1, right? And here 108, 108 is divisible. So the modulus is 11. And here the modulus is 1267, 7. Shit, so they did only just jumble around. 1 went here, 5 went here, 7 went here, and 11 went here. Why did that work? That is crazy. Which book is that? That is Ambience Incorporation. That is this Competitive Programmers Handbook. CPHB, Competitive Programmers and book. And you can read this on stream because this is open source in a way. Like this is free by the author. Author says you can use it however you want. Okay, so this thing is true. This claim by ChatGPT, where it is saying if we multiply all the numbers from A1 till psi for a given number m with a number x that is co-prime to m, then all of these modulus just jumble around. Why? Okay, we would have to write some general things to see that why. So the claim is this. Let's use this. That is very small. So that is not very small. That is actually extra large. So the proof is this. If we have a list A1, A2, A3, dot, 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 till A psi, we can represent psi with this thing. A psi m, it's modulus, it's mod with a number m. And if we multiply all of these numbers with x, right, then these moduluses just jumble around. They just jumble around here, here, there, everywhere. Why? If we represent this and x, the number also that we have, it is co-prime. It is co-prime with m. So how does that help us? It is co-prime. Notice the condition, co-primes. So you just reduce it modulo m first, and then so x can be bigger. No problem. Take all the numbers that are co-prime to m. It is exactly this. Now multiply each number u by x mod m, because x is a co-prime to m. X is a co-prime to m. Multiplication by x just rearranges the elements of u. If it is co-prime, how does that translate to something else? If it is co-prime. If it is co-prime, if X is co-prime, okay, okay. For a given number of m, for a given number m, there are only certain numbers from 1 to m that are co-prime with m, and that translates to modulus, that if I have any other number that is x or anything that is bigger than m, if I take its x's modulus with m, I would get one of these numbers from 1 to m that is co-prime with m. I should get that, because if I do not, if I get something else, and that remainder that I get from 1 to m, if that remainder is not a co-prime with m, then x also was not a co-prime with m. Does that make sense? I don't know. It feels like that I'm just at the cusp of understanding what this means. If I have a number m and x, okay, we can use our modulus arithmetic wheel here and some actual example. Let's say m equals 7. Our wheel would start at 0, then 1, 2, 3, 4, 5, and 6 at the end, right? It is a bit dyslexic. You can shift these a little bit closer. Cool. 4, 5, and 6. And here, 1 is co-prime. 1 is always co-prime with every number. 7 is shit, since 7 is a prime number. Every number here is co-prime with 7. If that is true, then m equals 7 is not a good example. We should go for something like 8. If m equals 8, that is not a very good circle. That is better. For m equals 8, our clock will start at 0, 1, it will go up till 7. 7. And here we have 1 is a co-prime. 1 is a co-prime with 8. 3 is a co-prime. 5 is a co-prime. And 7 is also a co-prime with 8. Okay. Okay. Now the thing is, if you were to take any number x and represent that number x onto this wheel, if x is a co-prime, then it must be represented at one of these values. If x is a co-prime, then it must be represented at one of these values. Makes sense. Makes sense. Even if, okay. So this claim is wrong. This claim is wrong. This is wrong. This is wrong. x is not forced to be represented as at some of these values. For example, if this is 8, then let's find a co-prime number whose remainder with 8 is 12. So with remainder 12, we would never have a co-prime. Wait, with remainder 2, no, 2 would never be a remainder. Let's say with 9, no, 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 9 is also not cool. For something like 6, 9 is a co-prime, not a co-prime. Oh, shit. Okay. The thing is this. X we are saying is co-prime. So X is co-prime and these numbers are also co-primes. That is when you prime factorize X into P1 power alpha 1 into P2 power alpha 2 dot dot dot, and you prime factorize any of these co-prime numbers from 1 till x, from 1 till m minus 1. You can, let's call it capital A, and if you prime factorize this number, p1 power alpha 1, p2 power alpha 2 dot dot dot, and if you multiply these, then this set, since we know that these two numbers are co-primes, therefore none of these numbers divide x, since divide m, none of these numbers divide m, since x and m are co-primes, and also none of these numbers divide m, since all of these are co-primes with m. Therefore, if you multiply all of these, that would still be a co-prime, right? Their product would also not divide m, because these numbers don't divide m, these numbers don't divide m, so their product would also not divide m. And what we have to prove now is that if we have, so the thing is, x into capital A, x into capital A would also be a co-prime, and all we have to do now is prove that if we have a co-prime number, it lands on one of these spots, and then we can move forward. We can at least, then we would have proved this line here. Now multiply each number u with x mod m, because x is co-prime. Multiplication by x just rearranges the elements. Yes, the same. Multiplication by x just rearranges the elements of u. It doesn't throw in a non-co-prime. This thing we can agree on. Like even right now, we can agree with this thing. It does not throw in a non-co-prime. That is something that we can agree with. What's going on here? We are reading about, not Hubris, we are reading about number theory from the competitive programmer's handbook, because you need number theory in competitive programming. And it has been quite long. 3 hours is a long time. But I want to get at least this part. Why this is true. Right. Okay. Or I could just agree with what ChatGPT is saying and not try to prove why it is correct, or make ChatGPT do the heavy lifting. Factors out this, and with this proof would make sense. This part about rearranges the elements. Why does it rearranges? This then leaves this. The group theory version, the set of integers co-prime to m under multiplication modulo m forms a group of size this. Makes sense. Lagrange theorem in group theory, the order of any element divides the order of the group. So for any x in this group, this equals this. The set of integers co-prime to m under multiplication modulo m forms a group of size this. That makes sense. The first line seems correct. The set of integers co-prime to m, that is a lot of integers, all the prime numbers except m, if m is a prime number. Under multiplication modulo m forms a group of size modulus m, of size psi m. Okay, which aligns with our claim that if we have a co-prime, it boils down to some of those numbers which are lower than m and are co-prime to m. In Lagrange's theorem, in group theory, the order of any element. Okay, now we are being introduced to a new thing, Lagrange's theorem in group theory. The order of any element divides the order of the group. And from whatever this is, we derive this directly. Okay, so we have, of course, we have some questions. First of all, why the rearranging thing? Why does it rearrange? And our hypothesis for why that could be is this. From 1 to m, there are psi m. From 1 to m, there are psi m numbers which are co-prime to m. And okay, given that if we have any number that is co-prime to m, should that have one of the modulo, should it that have should it have modulo m among modulo one of among modulo m, one of the numbers in the psi m group. Okay, the set of coprimes, the reduced residue system. Take all integers from m1 to m. Take all integers from 1 to m, among them exactly these are prime. Okay, we know that this is called the totient of m. Call this set, this thing. Okay, this is called the reduced residue system modulo. For m equals 12, we have 1, 5, 7, 11, and the size is 4. Okay, so this group is called reduced residue system modulo m. Okay, what happens if we multiply by a coprime? Suppose x is also coprime to m. Consider the set this, where we have multiplied one of these numbers with some number x, where x is a coprime. Claim this is the same as this. just rearranged. Yes. Why? If GCD AM equals 1, which we know by definition because this is a set. A is a set of numbers which are co-prime to M. So this is the thing by definition, and this is also the thing by definition. Then this is also the thing by definition, makes sense. Multiplying keeps us inside the co-prime set. So multiplying keeps us inside the co-prime set. Why? Why? Okay. If two results are congruent, yes, then they are congruent. Since x has a modular inverse, x has a modular inverse since it is coprime, yes. So we can divide this by modular inverse of x. Since there are psi m elements in both this and this, the sets must be identical. Okay. Why is this claim true? Okay, and there is also answering your question directly. Yes, every number x with GCD 1 is congruent modulo m exactly one member of the group UM. In fact, UM is like complete set of representatives of all coprime modulo m. For example, if m equals 20, then we have 1, 5, 1, 5, 7, 11. 1, 5, 7, 11. So any coprime integer collapses modulo m into one of those representatives. Why this matters, that is how Euclid's algorithm works, and we can find modular inverse. But why does it work? Why is this thing true? And specifically this line. This thing makes sense. Nope. Okay, this thing makes sense. This thing makes sense. And this thing makes sense since we originally had no copies, we would still have no duplicates. Makes sense, and there are this many elements. Okay, why is that true? GCD, this is cool. This is true by definition. Then GCD of this and this is also one. So multiplying keeps us inside the coprime set. Okay. Here the first claim makes sense that GCD XA n equals 1. But how does that lead to keeping us inside the co-prime set? Yep, it is not obvious at first glance. The situation. We wanted to justify this step. No, I know, I agree with this, but we do not agree with what comes next. That if this is true, then we are inside the co-prime set. Therefore, multiplying a by x keeps us inside the co-prime set. Yes. Why is that true? Take any prime factor p of m, prime factor. Prime factor. Prime factor. Okay, prime factor. It would not be a co-prime with them. Makes sense because it is literally a factor of m, except one. If GCD of a and m equals 1 for some co-prime number, then p does not divide a. makes sense. P does not divide A. If P is a factor of M and P does not divide A and A has no factor common with M, then P must not divide A. That makes sense. And if GCD of X and M equals 1, the same argument for that. So P does not divide X into A. Makes sense because it does not divide them individually, so it would not divide them combinedly also. Because if a prime does not divide X and does not divide A, it cannot suddenly divide their product. Makes sense. Since this holds for every prime divisor of M, no prime factor of M divides XA. Therefore, GCD would still be 1. Now, intuition in words. Shit, it ends very quickly. Being co-prime to M means you avoid all prime factors of M. Okay. Both A and X individually avoid them. Multiplying doesn't accidentally introduce new forbidden prime factors. So the product is still the same. So multiplication by coprime stays in a set of coprimes. Mhm. Being coprime to M means that you avoid all factors when A and B individually avoid them. Multiplying does not accidentally introduce new prime factors, so the product is still avoids them. The product still avoids them. A and A into B would give a GCD of 1 because there is no product. Because there is no prime number that divides M and also divides A into X because there is no prime number that divides them individually A and X. Okay. So the first claim you noticed is itself the justification. If both are coprimes, the product is 2, which exactly means the product is still in the coprime set. Okay. Okay. So the claim here you are making is that from the possible remainders that could be obtained with M, that is numbers from 1 to M minus 1, there is a certain subset of this set to which every number coprime to M modulo M can be reduced to. Yes, exactly. That is the right way to think about it. Let me restate clearly. Shit, that is all crazy. So, what book is this? Is it officially for CP? Yes, almost. Why do so much? Why so much math? Because reaching 2000 rating. Yeah, yeah, makes sense. Why do maths? And like, this is not even the big things in maths. Because later we are going to have Diophantine equations, which we will be solving using Euclid's algorithm extended version. And then we would have Chinese remainder theorem. We would have Lagrange, Lagrange's theorem and Pythagorean triplets, Zeckendorf's theorem, and Wilson's theorem. But before moving on, we have to make sure that we understand this thing. And yep, We are inside this thing, possibly all remainders. Okay, we are, I guess, almost there. Yes, exactly. That is the right way to think about it. All possible remainders of m. Uh, all possible remainders mod m. Okay. When you reduce any integer modulo m, it will have one of these values from 0 till m minus 1. That is the definition. That is the complete set of residue classes. Complete set of residue classes. Okay, we call this residue classes. We don't have to remember that. The co-prime subset. Yep, among them, some will be co-prime. That is a co-prime subset. Now, not all of those residue are co-primes because some of them would be prime factors of M and non-prime factors of M also. If we filter this set by the condition GCD of R, every going through R in M equals to 1, we get a smaller subset of psi M. Subset of size psi M because psi M is the number of co-primes from 1 to M. Makes sense. This subset is exactly the reduced residue system modular. Okay, so this thing is residue, and now we have reduced residue system modulo M because we have taken modulo M. No, we had modulo M to begin with. Anyways, denoted by UM. There is not even a single U in this whole thing. There is a U here and here and here. And then, okay, so UM is this a subset of all possible modulos, but these only have GCD equal to 1. Their GCD with M is 1. That is, they are co-prime with them. What happens to any co-prime integer? What happens to any co-prime integer? Any co-prime integer, either greater than M also. Okay. Take some x belonging to x integer with GCD 1. Reduce x modulo M. And why would it be in this subset UM? The result must be some R, some remainder, R is remainder from 0 till M minus 1. Yes, yes, that much we agree with. But GCD XM equals 1. Yes, by definition of X, that is true. By that, shit. Okay, shit. This is the exact thing that we use to find any Euclid's algorithm. Shit. Shit. Okay. Here we are trying to find GCD of A and B, and then GCD of A and B equals GCD of B and A modulus B. We are doing the same thing here. We have taken modulus of X. We have replaced X with modulus of X with M. Like you can write this as A modulus B and this thing as B. So initially we wanted to find GCD AB. Now we have replaced A modulus B and B. And we are doing the same thing here. That makes sense. So X has to be in one of the remainders, and one of the remainders which have a GCD equal to 1 is they are in this subset. There is no other remainder that gives a GCD of 1. So our number X, which is a coprime, has to be in this subset. That makes sense. That makes sense. That makes sense. That makes absolute sense. Okay. Because GCD is preserved under reduction modulo mod M. Yes, that is Euclid, Mr. Euclid, 300 BC. So the remainder R belongs to UM. Okay, we can agree with that. We can agree with that. What this means is for some number M, the possible remainders that we could get when we take any number x's modulus with m. The possible remainders that we could get is 0, 1, 2, 3 till m minus 1, and this is a whole set, right? This is set of possible remainders r equals this. Then we are saying that u of m is a subset of this whole set where every number is a co-prime with the number m till so this is a subset of all of those possible remainders where here every number is a co-prime of m. Co-prime means that their GCD, let's say some number is ri comma m, their GCD equals 1. That is the property which all of these numbers in this subset have, and also they are this is a subset of this whole set. And now the claim is, if we have some number x for which we have GCD of x with m equal to 1, if we have this, then we could replace this GCD with GCD of x remainder m equals 1, and this thing x remainder m has to be, this has to belong to this set, um subset, because it gives a remainder of 1, and that is true since this number gives a remainder of 1, and all the numbers lower than m which give a remainder of 1, which give a remainder, which give a GCD of 1 are in this set. Therefore, this x modulus m has to be belong to set. And that makes sense. That makes a lot of sense. That actually makes a sense. And that actually makes a lot of sense. Shit. But making the leap from this to this, this is obvious when we are using Euclid's algorithm to find GCD of two numbers. This thing is like, yes, obvious. We did this also earlier at some point, that we have done quite a few things here. Nope. Euclid's algorithm. We did do something with Euclid's algorithm at some point. Yep. Here we did, we saw why Euclid's algorithm works earlier, but connecting that with this, that is crazy. That makes sense. That makes sense. You could just replace x with x mod m in the GCD, and since it gives a remainder of 1, since it gives a GCD of 1, the remainder has to be in this set, set. That makes a lot of sense, actually. That makes a lot of sense. Are you on Mac? Yep, I am on Mac. And the setup is, my Mac is going to die. And I can charge it, which is pretty cool. It is charging now. So what have we established now? We have established this crazy thing, which does not make sense, but we have established that makes sense. This much, this much. So the remainder belongs to m. That is cool. Thus, every coprime integer reduced to one of the members of UM reduces to one of the members of UM. That makes a lot of sense. That makes a lot of sense. That actually makes a lot of sense. All residues and then coprime subset. Now pick any coprime number and it will reduce to U12. Makes sense. So our phrasing is spot on. That is cool. That is cool. And if that is true, then we have no problem with what was represented to us here. We have no problem with this because they are saying this jumble. Yes, this would also make sense. If 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 there is a subtlety, we said that whenever we multiply x with a, the modulus would stay in the set, but it does not mean that it will cover all of the elements in the set. It would cover should since we the rearrangement, right? That they are unique. This thing, this thing to keep us inside the covariance set. Yes, that we now understand why this thing is true. If two results are congruent x, a congruent b, right? If two results are the same, that is the problem. Then a congruent b, then a congruent b. Okay, so no duplicates, so they have to be exactly same. That makes sense. That makes sense. If the sets are same after multiplying every number with x, we know that xa will land on the set or inside the set, inside the set, and also that no two numbers are identical. Therefore, the sets have to be same. And if the set are same, then we have no problem with this proof. We can multiply them before x, we can multiply them after multiplying them with x, and this is what we have, and then we can take x common, this thing, and we take just modulus on both the sides, which would give us modulus with this would be 1 and modulus with this would be 1. Modulus would, no, we are not saying that, we are just multiplying all of these numbers with their inverses. Modulus inverse makes sense. So we are just cutting it off, yes. And that is cool. That is cool, and that is why this thing works. Makes sense. So now we know how this thing works. X, any number x that is co-prime with m, if we raise that number with the number of co-primes from 1 to m minus 1 for m, if we do that, then whatever number we get, its modulus m would be 1. That is cool. And then we have modular inverse, which I will not get into now. It has already been quite long. So in today's stream, we did number theory things and we explored some things. We figured out some derivations, why some certain formulas work. And so this was cool. This was actually cool. And there is like half of that chapter remaining. We only did about half. And the later half is more complicated than the first half. So I would do another maybe stream, or yeah, I would see what I can do. And this would be end of today's stream. Thank you for